Hello everyone. The topic of today's presentation is signal flow graph. It is an important topic in the control system, and I am Dr. Rathika, Professor, Electronics and Communication Engineering Department, PSN College of Engineering and Technology. This is the outline of my presentation. First we will see what is signal flow graph and why we have to go for signal flow graph. Then we will see some definitions and terminologies used, and finally we are going to see the Mason's gain formula to find the transfer function of a system with an example. First of all, what is signal flow graph? Say in control system, a transfer function will give the relationship between the output variable and the input variable. So there are many methodologies are available to find the transfer function. One of such methods is block diagram reduction. But for complex control system, the block diagram reduction is very difficult. So we have to go for an alternative method. So, which is developed by Samuel Jefferson Marshall. Since the block diagram reduction technique requires successive application of fundamental relationship in order to get the transfer function, he found a single formula to find the transfer function very easily for a complex control system. So, we are going for signal flow graph to find the transfer function of a system. So what is signal flow graph? A signal flow graph is a diagram that consists of nodes that are connected by branches. And a node is assigned to each variable, and branches are used to relate the different variables. Nodes are connected by directed branches. It depicts the flow of signal from one point of the system to another and gives the relationship among the signal. So this is an example of a signal flow graph. Here the yellow color point represents different types of nodes, and the black color lines represent the different branches. So next we will see what are the different terminologies used in signal flow graph. So for the first one is node. Node is nothing but a point that denotes a variable or a signal. Here I have represent R of S, C of S, V1 of S, V2 of S, etc., V3 of S. These are all the nodes. And the next terminology is branch. Branch is nothing but a unidirectional path that joins two nodes. So here this black color line join two nodes RS and VH of S. So this is called as one branch. And This line is another branch which connects the node V5 of S and V4 of S. So the relation between variable is written text to the direction of arrow. So G1 of S represents the text representing the direction of arrow. And the next one is forward path. So what is forward path means? It is a continuous sequence of branch that can be transferred from input node to output node without touching any node twice. That is called forward path. So what is important is it should not touch any node twice. So here you can see this flow is one forward path. So at a time we are touching only one node. So two node, you should not touch any node twice. So this is one forward path. And similarly you can take another forward path like this here, and you can go like this and in this way. So this is the second forward path. So similarly any different system have different number of paths. Next one is loop. Loop is nothing but a closed path that originate at one node and terminate at the same node. See, here this is a node. So it originates at V5 of S and travels in this way, and again a feedback path closes the direction to V5 of S. So this is called as a closed path. Again the flow should reach the original node. That is called loop. Next one is non-touching loops. So non-touching loops are loops with no common nodes or branches. So see, this is one loop and you can say this is another loop. So these two are two non-touching loops. So here there is no common node between the two loops. So this loop and this loop is taken as a two non-touching loops. And next one is input node, or you can call it as source. So input node is node having only one outgoing branch. See here R of S is called as input node because it is having only the outgoing branch, not an incoming branch. So R of S is considered as an input node. Next we will see some of the properties of signal flow graph. Usually the arithmetic equations are used to construct the signal flow graph and must be in the form of cause and effect relationship. And this signal flow graph is applicable to linear system only, and a node in a signal flow graph represent a variable or a signal related to the system, and a node adds the signal of all incoming branches and transmit the sum to all outgoing branches. And one more thing is the mixer node. A mixer node can be considered, it has both incoming and outgoing signals and can be treated as an output node by adding an outgoing branch of unity transmittance. That can be considered as a mixer node. The signal travelled along branches only in the marked direction. Either it can be marked in the forward direction or in the reverse direction, but the signal can only travel along with the marked direction, and when it travels it gets multiplied by the gain marked with the branches. So whenever the signal flow through a branch At the output node, we have to multiply the signal with the corresponding gain which is present in the branch. So these are some of the properties used in signal flow graph. And let us see some of the rules used. So this is the first rule. See here, incoming signal to a node through a branch is given by a product of signal at the previous node and the gain of the branch. So this only we have seen in the seen as a lost property. See here, this is the incoming signal to the node x2. So at node x2, the output can be represented as the signal at the previous node. So x1 is the signal at the previous node. So x1 should multiply with the gain of the branch. Here the gain of the branch is a. So at x2, what is the output means? x2 is equal to the product of gain with the signal at the previous node. So x2 is equal to a into x1. Similarly, for the next flow graph, here we are having two input and one output. x1 and x2 are the input to the x3 node. So how we can get the output at the x3 point is, see x3 is equal to, see here at this node the signal is x1, it should be multiplied by a1, so that you will get a1 into x1. And another input is x2, so you should multiply the corresponding gain in the branch, that is a2, so x2 into a2. So you have to add both the inputs, so x3 will get the output as a1 x1 plus a2 x2. And what is the next rule is, see, cascaded branches can be combined to give a single branch, and whose transmittance is equal to the product of the individual branch transmittance. So here we are having two cascaded branches. So here each branches have the gain A and B respectively. So we are going to combine this cascaded branch to a single branch. So what is the input is x1 and here x2. So combinedly we can take like this. You can multiply the gain present in the two branches. So you have to multiply so that it will give A into B. So x1 is the input node and x3 is the input node. It can be connected through a branch which is having a gain of AB. This is rule 2. And this is the third rule. So in the previous rule we have seen about the cascaded branch, and here we are seeing about the parallel branches. And the parallel branches may be represented by single branches whose transmittance is the sum of individual branch transmittance. See here x1 is the input node and x2 is the output node. And here there are two branches connecting parallelly, and the first branch is having gain A and the second branch is having gain B. So we have to add the transmittance. So at the output we will be getting x2, you can write x2 is equal to a1 plus b into x1. So whenever there are parallel branches, we have to add the transmittance to make it a single branch. And next one is rule 4. Here this is a mixed node. The mixed node can be eliminated by multiplying the transmittance of the outgoing branch to the transmittance of the all incoming branches to the mixed node. So here is a fourth rule. A mixed node can be eliminated by multiplying the transmittance of outgoing branch to the transmittance of all incoming branches to the mixed node. See, here there are two inputs x1 and x2 that gives an output at x3, and next this x3 is given as input to the x4. So this can be combined like there are two input x1 and x2. We are combining the gain of first and second branch, so it will become AC. We have to multiply these two gain AC, and similarly in the second branch also we should multiply B with C, so that you are getting the output at the node x4. So we can eliminate the mixer node like this. So this can be given in rule 4. Next one is rule 5. A loop can be eliminated by writing an equation. See, here there is a loop which starts from x1 and again it is ending with x2. So this how we can eliminate this means this loop alone can be eliminated by giving a gain like b by 1 minus c. B by 1 minus c. And here this x1 to x2 node is having again a gain of a. So we can multiply with that gain. So it becomes ab divided by 1 minus bc. This can be written in this way also. So we are keeping the first branch as it is, only this loop can be eliminated by using this equation, b by 1 minus bc. So these are the some of the rules used in signal flow graph. Next we will see Moissan's gain formula. See, as I have already discussed, the block diagram reduction technique is very difficult for complex control system. Also, it requires successive application of fundamental relationship in order to get the system transfer function. So, in order to avoid it, we are going for Moissan's rule, or we can say Moissan's gain formula for reducing a signal flow graph, which was derived by S.J. Moissan. He has given a single formula to find the transfer function of a system. So, this is the formula. Here the T represents the transfer function. T is equal to 1 by del summation of K Pk del K. So we will see 1 by 1. Here the T represents the transfer function of the system, and Pk represents the forward gain of kth forward path. So K represents the number of forward path, and this Pk represents forward path gain of kth forward path. And this K represents number of forward path in the signal flow graph. And here the del can be calculated by using this formula, that is equal to 1 minus sum of individual loop gains plus sum of gain products of all possible combination of two non-touching loops minus sum of gain products of all possible combination of 3 non-touching loops. It will go like that. So first we have to sum the individual loop gain, then sum of the gain product of all possible combination of 2 non-touching loops, then we have to find the sum of gain of product of all possible combination of 3 non-touching loops. It will go like that. And what is del k means, it also del for that part of the graph which is not touching kth forward path. So it should not touch the kth forward path. For that flow graph you have to find the del. That can be represented as del k. Let us see how we can find the transfer function of a system by using Moissan's gain formula. I have given an example here. See, this represents a flow graph of a system. So we will see how we can find the transfer function of this system by using Moissan's gain formula. So first we have to find how many number of forward paths is here. So here if you see, there are 2 forward paths there. See, the black color line represent 1 forward path, and the second forward path can be represented like this. So this is forward path 1 and this is forward path 2. So we cannot form any other forward path. Only there are 2 forward paths are there in this system. And now let us take the forward path gain be P1 and P2. See, as I have mentioned, here we are having 2 forward paths. By seeing this graph, you can clearly understand the system is having only 2 forward paths. So first we are going to find out the gain of the first forward path. See, for this forward path we are having gain like this. Here for this branch the gain is 1. For this branch the gain is G1. For this G2, G3 and G4, and finally we are having G5, and for output branch we are having only 1. The gain is 1. So we have to find out the forward gain path for path number 1, that is represented as P1. So P1 is equal to G1, G2, G3 into G4 into G5. So this is the forward path gain. Then we will consider the second forward path. For this, the gain can be represented as P2, which is given as G4, G5 and G6. So this is the gain of the second forward path. Next we will see individual loop gain. So if you see the graph, so here you are having 3 loops. See, this is loop number 1. This is loop second loop, and this one is third loop. So we are having 3 loops. Here P11, P21 and P31 represents the individual loop gain. While considering this loop 1, the gain can be calculated as minus G2 into H1. For the second closed loop, we can find the gain as minus G2, G3 and H2. Similarly for loop 3, the gain is minus G5 H3. Then we have to find the gain product of two non-touching loops. See here, this is one loop and this is another loop. These two loops are non-touching each other. So these two can be considered as two non-touching loop. Similarly, you can take this loop and this loop. So this also can be considered as two non-touching loops. So here we have found the gain of two non-touching loop. So for the first two non-touching loop, the gain can be represented as P12. So P12 is equal to P11 into P31. So if you multiply, you are getting G2 into G5 into H1 into H3. Similarly, for the second two non-touching loop, we have to calculate the gain that can be represented as P22. So after multiplying the gain of each loop, the output is G2, G3, G5, H2 and H3. This is the gain of the second two non-touching loop, which is represented as P22. So after calculating all this, we can substitute in the formula to find the del value. So del is equal to 1 minus P11 plus P21 plus P31, and for two non-touching loop it will be P12 plus P22. So you have to substitute all the value so that if you multiply and add it, you will get this value, and you have to find the del k. So del k is nothing but, you have already seen what is del k is. Del for that part of the graph which is not touching the kth part. So only one is available. That is, see, del 1 is which is not touching the first part, first forward path. So del 1 is equal to 1 because there is no part of the graph which is not touching the first forward path. So all the graph are touching the first forward path. So we can take del 1 is equal to 1 and del 2 is equal to 1 minus P11. So that can, so it does not touch, it should not touch the second forward path. So we can get only P11. So 1 minus G2 H1, it will give 1 plus G2 H1. So we have to substitute all the values because the k is 2 here. So 1 by del P1 del 1 plus P2 del 2. So why we have stopped up to 2 means here we have only 2 forward path. So after calculating all parameters, we have to substitute it in the formula, and finally we have to reduce it to get the transfer function, and this is the final transfer function we got for this system. So the system is represented in signal flow graph. If we represent a system in the signal flow graph, it is very easy for us to find the transfer function by using the Mason's gain formula. So this is applicable for complex control system also. I have explained one of the complex control system. So similarly, we can adopt this methodology for other systems also. Okay, thank you.